Hello, and welcome to Year 1 of A-Level Organics as taught by two current A-Level students. From our experience, this is one of the most intimidating, but arguably most interesting parts of A-Level chemistry. Let's jump right in and start by mentioning an idea introduced in GCSE, a hydrocarbon. A hydrocarbon is simply a compound made of only the elements carbon and hydrogen. Let's write an example of the molecular formula of a hydrocarbon. This is the molecular formula of butane. But you may have heard your teacher mention other kinds of formula in the past. What would those look like? These are all formulae for butane, which again has the molecular formula C4H10. But what about these other ones? Let's look at the empirical formula first. The empirical formula is simply the smallest whole number ratio of each element. So here we have C4H10, that is a ratio of 4 to 10, and if we just divide that by 2, we get a ratio of 2 to 5. That's our empirical formula. Next, we look at the structural and displayed formulae. The displayed formulae requires you to draw every bond, so we can show the complete shape and layout of the molecule. But a structural formula can show all that information without needing to draw any bonds. As we know it's a carbon chain, so we simply write each carbon, then the number of hydrogens bonded to it, and so forth until we reach the end of the chain. And you will notice with the structural formula and the displayed formula that we have 4 carbons, 10 hydrogens. With all that in mind, I think we're ready to move on to the skeletal formula, which is definitely my favorite because it allows you to convey all this information with just 3 straight lines. How does it do that? Well, each line is a carbon-carbon bond. The spaces at the end of the line are each a carbon atom. The beauty of this is that that's all we need to get everything we need out of this molecule. Because we know each carbon atom forms 4 bonds, and we can see how many carbon bonds this carbon atom has formed. And any bond that's not there, that's a hydrogen bond. So we see this one at the front is only joined to 1 carbon, so it must have 3 hydrogen bonds around it. This one has 2 carbon bonds attached, so it must have 2 hydrogens bond to it, and so forth. And that's why skeletal formula are a really quick and easy way to write organic molecules. Alright, the next thing on the specification is to know the terms homologous series and functional group. A homologous series can be best imagined as a family of similar organic molecules, in that they all share the same general formula and chemical properties. In GCSE, you encountered alkanes and alkenes, but in A-Level, we also focus on halogenoalkanes and alcohols. We will be covering each of these 4 different homologous series individually in our other videos in this playlist, as they are each rather complex. A functional group, on the other hand, is a much simpler idea. They are just the specific parts of a compound that give certain chemical properties. For example, an OH group or a CC double bond group. We'll now move on to the naming of organic molecules, and we'll use the skeletal formula as the carbon-hydrogen bonds will never matter for naming molecules in this specification. First, we look at how many carbon atoms are in the longest chain. In this case, that's 6. So we know we're going to use the prefix hex. Next, we look to see whether we have any functional groups besides CC single bonds and CH bonds. In this case, we don't have any. So we know that this molecule is an alkane. For alkanes, we add the suffix ane after what we have already written. In this case, we know that this molecule is hexane, but we are not finished yet. How do we add this branch up here into the name? Well, first we look at how many carbon atoms are in this branch. 1. So now we can add the prefix methyl onto our molecule's name at the front. We now know we have methylhexane, but there is one final thing we need to add. where is this branch attached? At first, you may be tempted to say that the branch is attached to the fifth carbon in the chain. However, this molecule is actually called 2-methylhexane. That's because whether it was attached to the fifth carbon or the second carbon, it would be exactly the same molecule. And we always use the smallest number. Now move on to how you name an alkene. Again, the first thing we look at is the longest carbon chain. In this case, that's 4, so we know we're using the prefix bute. Then we look at our functional groups. This time, we do have a CC double bond, which means we do have an alkene. For alkenes, we add the suffix -ene to the end. But be careful. We need to know where that double bond is. So we actually write but-1-ene, as the double bond is 1 from the end of the chain. Then we need to look at our branches again. We have 2 branches of 1, so we have 2 methyl branches. But how do we show where those branches are, and that there are 2 of them? Well, they're both bonded to the third carbon, so we're going to write 3,3 to show the location of each one, and then when we write methyl, we're going to add a di to the front of it. And that shows us that there are 2 branches, and this tells us where each one is, and we know it's but-1-ene from the double bond. This final, extremely complicated example should help us cover the remaining aspects of how to name organic molecules. As always, start by identifying the longest carbon chain. You may think the longest chain is 5 lines, but upon closer inspection, this is actually a carbon-oxygen bond, not a carbon-carbon bond. So we only have carbon atoms in these 5 spots, meaning we have the prefix pent. So we'll write that in. Next, we look at the functional groups. Because we have an OH functional group, we know we're dealing with an alcohol. And like with the alkene, we have to mention where that is. Here, the OH functional group is attached to the first carbon atom, so this is pent-1-ol. Now we'll look at the branches. We have methyl branches here and here. Again, because there are 2 of them, that means we're going to be using dimethyl. And because they're attached to the third and fourth branch, it's going to be 3,4-dimethyl pent-1-ol. At last, we can talk about how halogen atoms come into play for the naming of an organic molecule. I didn't mention them in the branches section because, like with this OH functional group, the chlorine atoms do not have another carbon here or here. Instead, they just replace 2 hydrogen atoms that would be bonded to this carbon that our skeletal formula does not show. With that said, you need to know the associated shorthands for the halogens chlorine, bromine, and iodine, which is simply chloro, bromo, and iodo, respectively. Then we just need to figure out how many chlorine atoms we have in this molecule. In this case 2, so it's dichloro. If there were 3, we'd call it trichloro, and if there were 4, we'd call it tetrachloro. Finally, we just need to know the locations of these 2 chlorine atoms. Both of them are on the second carbon, so this is 2, 2, dichloro, 3, 4, dimethyl, pent-1-ol. That was a lot. But fortunately, naming molecules comes easily with a bit of practice, and you'll be doing it constantly throughout this topic. It's finally time to move on to something different. Reactions. There are 7 ways to classify a reaction that we care about in organic chemistry at this stage. So let's go through them quickly. Bear in mind that some of them are not necessarily mutually exclusive. Addition is exactly what it sounds like. It is when an atom or group of atoms is added to a molecule. Elimination is the opposite. It is when an atom or group of atoms are removed from a molecule. Substitution is a similar idea. It is when we replace an atom or group of atoms with a different atom or group of atoms. Often, this is because of an elimination reaction followed by an addition reaction. You should be familiar with the acronym oil rig from GCSE. Oxidation is the loss of electrons, and reduction is the gaining of electrons. That is completely true, but at A-level we also have other ways to define oxidation and reduction. For organic chemistry, the simplest way to think of oxidation is the replacing of a carbon's carbon-hydrogen bond with any other bond, whether to another carbon, an oxygen, a halogen, or nitrogen. Reduction is the opposite, where a carbon-hydrogen bond replaces any other kind of bond, in this case, a carbon-carbon double bond. Hydrolysis is an easy type of reaction to define if we simply look at its name. Hydro obviously means water, and lysis means to separate or break. Therefore, any reaction where a water molecule has to break apart is actually a hydrolysis reaction. This example here, and the other version of the same reaction I wrote beneath, is actually the same example I used for elimination, showing once again that one reaction can have multiple classifications. The seventh type of reaction is polymerization, which is also another thing encountered at GCSE. It is where an organic compound reacts with itself to form an extremely large chain-like molecule. We'll be talking more about polymerization in the alkenes video. For the finishing two spec points in this video, we're going back to formulae. More specifically, isomerism. Isomerism is the idea that multiple different molecules can have the same molecular formula. For example, the molecular formula C4H8. All of these molecules on the screen have 4 carbon atoms and 8 hydrogen atoms, and yet all of them have different names. We call this structural isomerism. In fact, if we didn't have different names, they couldn't be structural isomers. Interestingly, the molecules you see on the screen are actually all of the structural isomers of C4H8. You may think that can't be true, because what about butyriene or 2-methylpropytuene? Well, let's draw those out. Butyriene would look like this, and that's exactly the same as butyronene. The double bond is 1 from the end, so it's just butyronene. If we look at 2-methylpropytuene, it doesn't matter where we put the double bond, it's all 1 from the end. That's why we don't even specify where the double bond is. It would make no difference either way. So, isomers are a little bit complicated, and you need to get extremely familiar with them, because draw out all the structural isomers of X molecular formula is a very common exam question. For the last spec point in this video, you must understand that there is another type of isomerism besides structural isomerism, one that only matters when you have a double bond. Following all the rules so far, these molecules are both named butyriene, and they are the same structural isomer. Their bonding is identical. The thing with double bonds is that unlike single bonds, both atoms involved are locked into place. This means that the molecule cannot rotate, and suddenly the positions of these other carbon atoms relative to the position of the carbon atoms in the double bond affect its chemical properties and really matter. We call this idea stereoisomerism. There are 2 ways to name molecules where stereoisomerism is relevant. The first way to name stereoisomers is the cis-trans system. It doesn't work very well for more complex molecules, but at this stage that doesn't matter. Basically, trans means across, and cis means the opposite. In this molecule here, the bonds we care about, as in the bonds that aren't hydrogen, go across the molecule. So we call this trans-butene. In this other molecules, the carbon bonds don't go across the double bond, so we call this cis-butene. But there's another system for naming stereoisomers. We call that one the EZ system. E stands for the German word entgehen, which means to avoid, miss, or escape. Z stands for the German word zusammen, which means together. Here, the carbon atoms are avoiding each other, so this is E-butene. Here, these carbon atoms are on the same side, so this is Z-butene. It's that straightforward. With that, we have reached the end of the first video in the series. We're going to start talking about alkanes in video 2. See you there.